Hi, my name is Katherine Boerckel.
And my name is Allison Grove.
We are ninth grade students at Washington Liberty High School.
We thank you for your time and present to you our study, The Effect of Weather Patterns on the Spread of Airborne Plastics.
In the past year, we have become interested in renewable and recycled materials to create textiles since the trending fast fashion industry is contributing to air pollution.
As discovered in our background research, scientists have found the presence of polyester and other fibers thought to be from low-cost textiles in airborne plastics.
Our background research also looked at studies that discovered airborne plastics in the atmosphere of underpopulated areas, including U.S. national parks in the Swiss Alps. This led us to wonder, how do these common plastics spread through the atmosphere and end up in rural locations such as national parks?
Scientists have discovered that winds and rainstorms increase the distance and speed that airborne plastics traveled from a point of origin to a point of reception.
This diagram shows how wind can increase the transport of plastic debris from cities into the Earth's oceans and natural habitats.
We assessed articles discussing the transmission of plastic pollutants and the extensive distances they had traveled to rural locations such as national parks. Many also discussed the large quantities of airborne plastics derived from large U.S. cities ending up in rural areas.
Since we live very close to Washington, D.C., as well as Shenandoah National Park, we were interested to see if our data would demonstrate this pattern as well.
The purpose of our experiment was to analyze how far air masses travel from urban to rural national park locations.
We also wanted to observe any patterns in the distances traveled. These may be caused by prevailing winds, as shown in this map that is demonstrating wind patterns and deposition of atmospheric debris and pollution.
And we evaluated points of origin and wondered, are airborne plastics traveling from large cities to these rural areas as seen in our background research?
Our hypothesis stated that if high concentrations of airborne plastics are found in urban areas, then they will travel and affect ecosystems in less populated areas such as national parks because of weather patterns.
Our experiment looked at the distance that airborne plastics traveled to 5 selected national park locations across the U.S. over the span of 7 days.
Our most crucial resource in this study was the high split trajectory model provided by the National Oceanic and Atmospheric Administration.
This program was the basis for the project design and determined the variables of the study based on the information that was provided by this model, which were the locations of derivation for each national park's daily air mass.
This indicated that our study would examine the distance that airborne plastics traveled from point of origination to point of reception.
Finally, the high-split model provided and computed all primary data.
A constraint that the study ran into was misinterpreted abilities of the high split model. We planned on tracking weather patterns' effect on amounts of airborne plastics, but we ended up measuring the distance that airborne plastics traveled while still factoring weather patterns in.
This constraint could have been minimized through more thorough background knowledge regarding resources used before designing the experiment.
Since this project was data-based, using online resources, minimal materials were occupied. We used the high split database model provided by the National Oceanic and Atmospheric Administration.
We also used Microsoft Excel and Google Maps, both of which were used to calculate and condense raw data.
The initial step of this procedure was to download the high split model.
Once the high-split model was downloaded, we were able to select national park points of reception based on locations that the model provided.
The data was then recorded regarding each air mass's point of origination.
Finally, the distance from each point of origin to each point of reception was calculated using Google Earth.
This summative data table displays the mean distance and standard deviation that airborne plastics traveled from urban to the 5 selected national park locations over the span of 7 days.
This graph displays the mean values and standard deviation values using error bars in our data. The bar graph allows us to see some of the statistical differences and similarities between each experimental group.
The results of our study demonstrated that on average, airborne plastics were traveling between 166.7 miles and 760.1 miles from urban to the locations to the selected national park locations.
A noticed trend in the data was the average miles traveled between the experimental groups Isle Royale National Park, which had an average of 585.6 miles, Acadia National Park, which had an average of 500 miles, and Everglades National Park, which had an average of 760.1 miles. The average miles traveled of these experimental groups ranged from 500 miles to 760.1 miles. Based on information discussed in our background research, we can infer that this trend may be due to similar weather patterns affecting these locations.
The pattern evaluated in our data demonstrated a possible advantage of the model because this trend could be used to motivate a future study that examines how weather patterns specifically affect the trajectory of airborne plastics.
On the other hand, this trend in the data also demonstrated a possible limitation because the high-split trajectory model's algorithm may have errors, possibly creating trends in the data.
The components of this data trend are underlined on this table.
The null hypothesis stated that if high concentrations of airborne plastics are found in urban areas, then they will not travel or affect the levels of airborne plastics in less populated areas because of weather patterns.
The p-value was 1e to the negative 8, demonstrating that the data is indeed significantly different. Therefore, the null hypothesis is rejected.
Based on the data analysis, the data supported the idea that airborne plastics are traveling extensive distances to areas like national parks through the atmosphere.
The data also supported the purpose behind the high-split model, part of which is to use the resource in an effort to examine airborne plastics travel to protected areas of the United States, and maybe eventually use this research to improve the use of plastic.
The common routes that air masses traveled to each national park location are displayed on this map.
In conclusion, the average distance in miles that airborne plastics traveled from urban locations to national park locations ranged from 166.7 miles and 760.1 miles.
This data supported the hypothesis as it shows that airborne plastics had consistently traveled immense distances to the national parks.
A future study could look in depth at weather patterns' effect on the amounts of airborne plastics in national parks. A question that could lead this future study is, how do weather patterns affect or create trends in the amounts of airborne plastics in selected locations?
Some unexpected factors in this study were that the high-split model only provided a specific selection of locations to choose from.
Due to this unexpected factor, initial selections regarding points of reception therefore had to be reevaluated.
Also, when reselecting locations, we had to ensure that the locations were not in very close proximity in order to avoid producing data that is statistically alike.
A major takeaway from this study is that the plastics we use in everyday life, found in clothing and essentials, can end up in the air we breathe in protected areas across the United States. This could lead to harmful health effects on humans and the environment.
The data concluded from the study could be applied in the future to spread awareness about airborne plastics in protected areas of the United States.
Finally, this data could lead to policies that promote the use of renewable resources to produce essential items that currently use plastics. Thank you very much for your time.
Please inform us of any questions you have.